Welcome back to Unit 8. In Part 4, we're going to look at conservation of energy. So when can we say that energy is conserved? Or in other words, when can we say that the energy of a system is constant? That requires that no non-conservative forces are doing work on the system. If we think about the concept of work, we can divide it into two pieces: the work due to non-conservative forces plus the work due to conservative forces. And that has to equal the change in kinetic energy. For energy to be conserved, we have to assume this goes to zero. As we learned in the last unit, or last part, work due to conservative forces is the negative of the change in potential energy. Separating this out and rearranging gives me that the initial kinetic energy plus the initial potential energy has to equal the final potential energy plus the final potential energy, or in other words, the initial energy has to equal the final energy, and I have energy being conserved. There are two classic systems where we think about using conservation of energy. We're going to look at those two. The first one is the mass on a string, otherwise known as a pendulum. If you open that link, it leads to this simulation. And we're going to go click on the energy one. So here you can see I have a pendulum. I have gotten rid of friction. So I've gotten rid of the non-conservative forces. And we'll slow it down so you can see it. As it swings, you can see the energy changes from potential to kinetic and then back to potential. The potential energy is greatest at either end of the motion. That is because the pendulum is as high above its lowest point as it's going to be. The kinetic energy at these endpoints is zero because it has to stop momentarily in order to turn around. At the bottom of the motion, the kinetic energy is maximized and the potential energy is minimized, in this case zero, because this simulation assumes that the potential energy at the bottom of the motion will be zero. If I turn friction back on, you can see that this bar for E thermal is growing. Okay, and I get corresponding bar in my total energy here. If you also notice, the pendulum is no longer swinging up quite as high. This is more obvious if I bring things up to full speed. Thermal energy slowly grows. Potential energy and kinetic energy no longer have as much ability to, they're no longer as big. And the pendulum slowly decays down to where it won't oscillate any longer. Returning to our PowerPoint presentation, the other classic system is the mass on a spring. If you look at, or if you click on that link, you'll get to this simulation. Again, I'm going to start with damping, or in other words, friction down to zero, and I'm going to hang a mass on here. Wherever I put this height-wise determines what the total energy is, and it is some combination of both elastic potential energy and gravitational potential energy. The elastic potential energy is zero at the point where the spring is unstretched, so that would be about here. So you can see if I go above it, I've given it elastic potential energy because the spring is compressed. And if I go below it, we have elastic potential energy because the spring is stretched. But right at this line, my elastic potential energy goes to 0. I have a 0 for gravitational potential energy somewhere down here. Oh, at the blue line marked height equals 0. Look at that. If I go below it, I've actually got negative gravitational potential energy, which is kind of fun. Okay, well, let's give it a little bit of total energy here. Oh, maybe a little bit more, because most of that energy is contained in the gravitational potential energy, which we're really not changing about. So let's make it really oscillate by giving it some more elastic potential energy. Okay. We see that we always have gravitational potential energy because we never get all the way down to the height equals 0 mark. If I slow it down, you can see that kinetic energy goes to 0 at either endpoint. Again, this is because it has to stop momentarily in order to change direction. And elastic potential energy changes, but it goes to 0 again at this line that we put in where the spring was unstretched. So the question in the PowerPoint slide was asking, when is each type of energy present, maximized, and minimized? So gravitational potential energy in this case is always present because we have height equals 0 down here at this blue line, and we never get down to it. It is maximized when the mass is as far as possible above that line. Kinetic energy is maximized at some point in the middle. It's not 100% clear where that point is in terms of the other energies. It's minimized at 0 at either end. Elastic potential energy is 0 when the spring is unstretched. It is maximized when it is stretched or compressed as much as possible, and everywhere else there's some of it present. Now again, if I turn on damping, this time I'm just going to go for lots, we again see that our energy changes from being elastic and potential, our elastic potential, gravitational potential, and kinetic potential, and instead becomes thermal energy. Let's now apply this to just a falling object. So we're going to look at a 5-kilogram ball falling from rest from a height of 100 meters. I like to draw a picture. It's not a very involved picture, but I'm going to let the ground be my 0 height location. I'm looking at part B and seeing I need some spot in the middle, but I don't know what height that is at. And then I have part the problem statement, which tells me I start at 100 meters. I'm also told that at this location, V equals 0. At this location, we're moving downward at 30 meters per second. And the last thing it wants to know is how fast is it moving right before it hits the ground. So right before it hits the ground, it's still going to be moving downward, but we don't know how fast. To find the total energy, I want to look at the top. At the top, which I'm going to call point A, point B, point C, my gravitational potential energy plus my kinetic energy at A, but my kinetic energy at A is 0 because it's not moving, so I can not think about it. My gravitational potential energy will be the mass times the acceleration due to gravity times the height at point A, which will be 5 kilograms times 9.8 meters per second squared times 100 meters, and that equals 4,900 joules. Part B. At what height is it moving at 30 meters per second? So we're going to assume that energy is conserved, so we don't have to worry about air resistance or anything like that on this object. The point where it's moving at 30 meters per second is the point I defined as B. So my total energy has to equal the kinetic energy at point B plus the gravitational potential energy. Oops, I got ahead of myself there a minute. At point B. Well, it shall be 1/2 times the mass, or times the velocity at B squared plus mg times the height at B, which is what we want to find. Our total energy we just found. This has to equal 4,900 joules. So that'll be 1/2 times 5 kilograms times my 30 meters per second squared plus 5 kilograms times 9.8 meters per second squared times my height at B. Multiplying my kinetic energy term together and then subtracting it from 4,900 results in 2,650 joules equals 49 kilogram meter per second squared times YB. Solving for YB gives me 54.1 meters. Go up and add my box there. Lastly, we want to know how fast is it moving before it hits the ground. So in this case, E total will equal the kinetic energy at part C plus the kinetic energy, not kinetic, let's try again, plus the gravitational potential energy at part C. This one goes to 0 because point Z is where we defined the height equal to 0. Okay, and I want to stress here, we are looking at the moment before it hits the ground, not when it's actually hitting the ground. So if you want to think about the height being just a smidge above 0, that's fine, but still for all intents and purposes, that gravitational potential energy will equal 0. So our 4,900 joules equals 1/2 times 5 kilograms times the velocity at C squared. Solving for the velocity at C, that equals 44.3 meters per second. This completes this part of Unit 8.